Good evening, one and all. Myself, Yashvi Sheth, and today it is the seventh live session for the course Basic Principle and Calculations in Chemical Engineering, taught by Professor Subrato Majumdar from IIT Guwahati. So, starting with the brief of the lectures that were taught. Um, so, basically, in the last week, whatever was covered was the basics of energy and some definitions of energy and energy balance, like how you apply energy balance for various systems. So, what is the basic of energy balance? It is nothing but accumulation of energy equals to input of the energy to the system minus output of the output of energy from the system. So here there is one condition that there is no generation or consumption of energy in the system. And if you simplify that energy balance, then what will come out is this equation. Here this Ws is the shaft work. It is the work that a system can produce. So it depends on the pressure drop. It depends on the flow, like the kinetic energy that system has, the potential energy with the system, and also there is some kind of, because not all systems are ideal, so there will be some amount of loss in the form of friction or heat loss or any kind of dissipation, which is denoted here by F. So this is the generalized energy balance equation, and it is written over here. Now this is the energy balance, like mechanical energy balance. For that we usually consider internal energy, we usually consider kinetic energy and potential energy, and we do not take into account of any internal energy change or heat transfer due to like any other heat transfer or chemical reactions. So this is it. Now if we want to further simplify this equation, this is the generalized equation, and if we want to further simplify this equation, then what can happen is, so this is nothing but a Bernoulli's equation, where we assume that there is no viscous heat dissipation, or it is very negligible as compared to what other terms are. In that case we can apply Bernoulli's equation, and also the frictional loss and shaft work are zero. So in that case what remains is delta P by rho plus delta U square by 2 plus G delta Z is equals to 0, which is nothing but Bernoulli's equation. Now this equation is usually applied for incompressible fluids. Okay, system needs to be in, there should be fluid flowing, and what incompressible fluid means, it density of fluid should be constant. So based on these kind of assumptions, Bernoulli's equation help you apply energy balance. So it is nothing but energy balance. It can be applied for any kind of system which has which deals with incompressible fluids, and in which fluid is in motion or fluid is flowing. So moving forward, there is another kind of energy balance, or like which I talked about earlier also, which was enthalpy. So what is the enthalpy? It is nothing but the total heat content of a system, which includes internal energy plus any sort of another energy due to temperature that a system possesses, which is represented in the form of product of P into V. So H equals to nothing but U plus PV, and delta H in terms of internal energy. This was all talked about, discussed in previous lecture. So delta H is nothing but delta U plus P delta V. So we usually calculate enthalpy at constant pressure. So that is why delta P into V term gets eliminated from this equation. So now if you have any system in which there can be two things happening. There is first temperature change of the components that are present in the system, and there can be phase change, like from solid to liquid or liquid to solid, gas liquid phase change, etc. So in that case, how do you apply energy balance? So say for example, if you have a process unit denoted here, and the input stream has two components and the output stream has the same component, here there is one assumption that no reaction is occurring. This is the general heat enthalpy balance enthalpy equation. When you have some temperature change, then it is nothing but delta H equals to, this is the heat of formation of that particular compound, delta HF naught plus T reference to T Cp dt. Now if you have certain number of like n1 moles of component 1, n2 moles of component 2, then the enthalpy, since it is represented as any energy, like energy per unit mole, then you can multiply with number of moles. And if you want to find out change in enthalpy, then what you will do, delta H of the system equals to final minus initial. So it is nothing but the enthalpy of output, delta H output minus delta H of input. So delta HF naught will get cancelled out because the same components are present with, because we have considered that there is no reaction occurring. So delta HF naught will get cancelled out, and here it will remain as TF Cp dt. Like here for a mixture, what will be the Cp? It will be N1 Cp1 plus N2 Cp2. Like it has to be in like N1 by N1 plus N2 mole fraction. So this is how you represent Cp here, and minus T reference. Let's say this is the initial temperature, Cp dt. So what remains is from T initial to Tf, Cp dt. So this is what we had derived earlier. Now moving forward, like if there is phase change, then I had discussed at that time also, like how temperature profile, how temperature changes during the entire transformation. So for example, if you have here we have taken an example of water. Suppose you have ice at let's say minus whatever degree, minus 10 degrees centigrade, and the melting point of ice is 0 degrees centigrade. So during that transformation, there will be some amount of heat which will be absorbed for ice to melt. So it will go from minus 10 to 0 degrees Celsius. Just a second. Yeah, so it will go from minus 10 degrees Celsius to 0 degrees Celsius, which is nothing but melting of ice to liquid water. Now, no, it is just the temperature change, which is by absorption of heat. Now once it comes at 0 degree, which is the freezing point or melting point, now at this point it will there is some heat of fusion which will be absorbed during the melting of ice to liquid water. So at this, during this transformation, this much amount of enthalpy or heat will be absorbed, but the temperature will remain constant, and it will have solid plus liquid, both the phases. Now again, if you keep on supplying heat, then entire solid will get converted into the liquid phase. And now once all the solid has transformed into liquid, then again the temperature will start raising if you keep on supplying heat till the boiling point. This is the boiling point, which is 100 degree for water. So till the boiling point, the liquid will keep the temperature of liquid will keep on rising, and after reaching the boiling point, again if you keep on supplying some sort of heat, then that heat will be used to convert liquid water into gaseous form, which is nothing but heat of vaporization. So during that phase also there is constant temperature is maintained, and further after transformation to gas, the temperature will rise. So this is how the profile looks like for the transformation of any from solid till gas. The amount of heat that will be required will change from one, like for water it will have some heat, and for like heat of vaporization, and if there is some another liquid, say another substance, say for example ethanol, then for ethanol, heat of vaporization will be something else. So it depends on chemical to chemical, but the sort of the nature or the trend of the profile or the profile will remain same. So moving forward, we will start with the assignment for week 7. So the first question is, which one of the following is not a mechanical energy? So as I discussed earlier, mechanical energy in the definition itself, it states that it usually includes kinetic energy and potential energy. So work is not included in in the calculation of mechanical energy. So work is the answer here. Next question is, Bernoulli's equation for fluid flow refers to dash. So during the during the derivation or the equation that I stated for Bernoulli's equation, we have certain assumptions where we apply energy balance. This is the energy balance which is applied for a flowing system. So and the flow has to be under the influence of some potential gradient, which is represented by this term. So Bernoulli's equation for fluid flow refers to the mechanical energy balance in potential flow instead of any as compared to other options. Next question is, which of the following equation relates the pressure with velocity and the height of fluid? So obviously the Bernoulli's equation is the correct answer, as I had mentioned the equation. If you look into the other options, then equation of continuity is rho A into V is equals to constant, which is related with density and the velocity. Now Gibbs free energy equation is nothing but delta G equals to RT ln K. So there is no such term of pressure and velocity in this case. An equation of motion is all related about velocity or motion, which does not consider any pressure or height of fluid. So correct answer is Bernoulli's equation. Next question is which one of the following is applicable for Bernoulli's equation? So as I had mentioned, there are certain assumptions for Bernoulli's equation, which is nothing but flow has to be steady, fluid must be incompressible, and the frictional or viscous force are negligible. So in this case, all other options are observed to be not correct. So Bernoulli's equation is usually applied for ideal incompressible fluid. Next question is an airplane flies through the sky where the air flows horizontally over the airplane wing at a speed of let's say this is the wing, and at the top it is having 110 meter per second of velocity, and at the bottom it is having 80 meter per second. So let's say this is 1 and this is 2, and the air density rho is given as 1.2 kg per meter cube. Now the wing has the length of, like this is the length, so it is 9 meter, and this thickness is, like the width is 3 meter. So what is the pressure difference on the two sides of the wing? So if you want to find the pressure difference, then obviously we will apply Bernoulli's equation, delta P by rho plus delta U square by 2 plus d delta Z. Now since this term can be neglected here, because like, or you can keep delta Z as 3 meters. Now since as compared to other terms this 3 is very small, you can obviously neglect that. It has to be 0. So delta P by rho equals to minus U square by 2. And if you calculate, like U will be 80 square minus 110 square divided by 2, minus of this into 1.2. Now if you calculate this, the delta P or the pressure difference across the wing will come out to be 3420 pascals. Now yeah, so everything is in SI, so delta P will be in Pascal. Next question is Bernoulli's equation is based on the conservation of here if we look into the equation, then this term represents the uh, energy which is corresponding to the kinetic energy of fluid. This term represents the potential energy, and also you can relate pressure with energy or pressure with energy. So basically it is a kind of energy balance. So energy is the correct answer here. Bernoulli's equation is applicable for fluids as it was discussed earlier. Now if the system is not rising or falling, then delta P should be dash. So if we look into the equation of Bernoulli's equation, then since it is not rising, delta Z is 0. So this term is 0. And since there is no motion mentioned here, so U also is assumed to be 0, which means delta P is 0. Next question is, a cylinder fitted with a movable piston is filled with gas. The amount of 20.9 kilojoule of heat is transferred to gas to raise the temperature by 150 degrees Celsius. So here you have a cylinder in which this is the piston and gas is filled here. Now if you are supplying some sort of heat which is 20.920 kilojoule and its temperature increases by 150 degrees Celsius. So now since you are applying some heat to the system, the molecules of gas, it will have more energy, and that energy will result into more collision between, like, faster mobility of gas molecules, and like temperature increases, the internal energy of gas increases, which results into higher or more vibrations and collisions of the molecules of gas. So now this will result into like expansion of gas, and it will try to move the piston upwards. So that will again try to attain obviously the equilibrium. So certain amount of work has been done by by this gas to move the piston upwards, which is given or mentioned as 50 joules. So and a new equilibrium, say for example here the piston has been shifted. So what change in internal energy of the system is observed? So to find out the change in internal energy, you apply first law of thermodynamics, which is nothing but delta U equals to Q minus W. Here Q is the amount of heat added to the system, and W is the amount of work done by the system. Okay, so here delta U will come out to be, Q is given as 20.92 kilojoules. Here work done is in joules, so you divide work by 1000 to convert into kilojoule, and if you subtract this, like if you solve this, the answer of like delta U will come out to be 20.870 kilojoule. Next question is, the unit of energy is dash. So energy is nothing but represented as kg meter square per second square. And if you look into the options, like joule per second is nothing but watt, which is the unit of power. Newton per second will come out to be, what is Newton? Kg meter per second square. And if you again divide it with second, then it will be kg meter per second cube. So obviously this is not the correct answer. This also is not the correct answer. Now if you see Newton into meter, then Newton is kg meter per second square into, if you multiply with meter, then it will be kg meter square per second square. So Newton into meter is nothing but corresponding to joules, which is the unit of energy. Next question is the process of heating a liquid mixture to form vapor and then cooling it to get a pure component is known as. So, so we will try to understand each and every process which is mentioned in the options. The first process is evaporation. Then what is evaporation? If evaporation is nothing but to concentrate any solution that you have. Say for example, you have a sugar solution or you have any fruit juice. So in the industry, if you want to like juice is prepared in the industry and the fruit juice that you get in the market, it is usually it is concentrated. So what you do, say for example, you have dilute solution in the form of, let's say, fruit juice. So you supply that and you try to concentrate that in the evaporator. Then what happens is certain amount of water present in that solution, it is converted into vapor and it is recovered, and what left is the concentration of solute increases. So this is the aim that you want to achieve in evaporation, which is to concentrate the solution and increase the solute concentration. So this also you apply during crystallization also, like where you need super saturation. So you first try to concentrate the solution that you in which the solute needs to be precipitated, like from which the solute needs to be precipitated. Next is the distillation. So distillation is obviously the answer. Like distillation is the process where say for example you have a feed in which it will be a mixture of liquids which has difference in volatility or difference in, you can say, boiling point. So for example you have ethanol and water. So ethanol has a boiling point around 77 or 78 degrees centigrade and water has around 100, like 100 degrees Celsius. So based on the difference in this boiling point, what happens is ethanol will start boiling faster, it will get converted into vapor, and that vapor will be recovered. So and because like what happened is, if you supply heat, then ethanol tend to evaporate faster, ethanol tend to boil faster as compared to water. So if you apply certain amount of residence time in the form of length in the column, so more and more vapor will travel upward, and as like certain amount of vapor water will also get vaporized, but as it moves upward, certain there will be interaction or heat exchange between water and ethanol, and obviously water will condense faster, so water will tend to go downward because it is still in the liquid form. So you will get water or high boiling liquid at bottom and low boiling liquid at the top. So by this way there will be certain equilibrium in the column, and based on that certain amount of height you provide so that you convert the mixture into pure liquids. So here you convert a liquid mixture to vapor form and then again cool to get the pure component. So this is nothing but distillation. Next option is drying. So drying is a unit operation which is carried out in any industry. where you have any sort of solid which has some moisture content, and to make the product saleable in the market, or depending on what is required, you want to remove water or moisture from that solid. So you try to evaporate that water from the solid, which is done by drying. Next process mentioned here is crystallization. So crystallization is nothing but a process in which you try to get solid precipitated by cooling and supersaturation from the solution. Say for example, if you have a sugar solution, and like if you keep that sugar and you dissolve excess of sugar in water. Now if you keep cool down the temperature, cool down the solution by keeping it in refrigerator, then what will happen, you may observe some amount of crystals of sugar in that solution. So that is nothing but crystallization process, where you try to solidify or precipitate the solute which is present in the solution. Next question is, a binary distillation column separates 100 mole per hour of a feed mixture into distillate and residue. So you have a distillation column here, in which the feed is going in. Feed has flow rate of 100 moles per hour. It is separated into distillate at top, D, and residue at bottom. So you need to find out the distillate and residue flow rate. Another data that you have been given is the feed mole fraction. So XF is 0.5, and the mole fraction of that component in distillate is 0.98, and in residue it is 0.05. So to find out the residue and the distillate flow rate, what you do is you apply the material balance. Like material balance will be 2, overall mass balance, and component wise mass balance. So firstly, overall mass balance is nothing but whatever goes in, and say whatever comes out, you just take that much into account. So what is going in is input equals to output. That is the overall mass balance. So in like for this system, feed is the input, which is nothing but F. That is equals to the output, which is D and W. So output is D plus W. So this is the equation 1. So here you know F. So 100 equals to D plus W. So this is the first equation. Now if you want to apply component wise mass balance, so you apply input of component 1 equals to output of component 2. So input of component 1 is in the form of feed, which has mole fraction 0.5. So out of 100 mole per hour of feed, 50% or 50 mole percent is the substance which is mentioned here. So 0.5, like you can write XF into F equals to what will come out in the distillate is XD into D, because D is the total flow rate which is coming out in distillate, and XD is the mole fraction of mole fraction of component 1. Here in the bottom it is the XW, and W is the flow rate. So output will be XD into D plus xw into w. Now if you substitute the values, xf is 0.5 into 100 equals to xt is given as 0.98, d is to be found out, xw is 0.05, and w is also need to be found out. So this is equation number 2. Now if you solve equation 1 and 2 by cross multiplication, d will come out to be 48.38 mole per hour. It has to be same as what feed unit is, and w comes out to be 51.61 moles per hour. You can solve by yourself by solving these two equations. Moving forward, next question is, in distillation the overhead product contains dash. So what you do in distillation is, you have a liquid mixture and you try to separate and distillate and residue like bottom. So there can be n number of n components also. It can start from binary mixture to n number of components. And one of the example where multiple components are present is nothing but crude oil, from which you try to extract all the um, petroleum products. So based on what type of product you want to get from the distillation column, say for example you just want one product out of um, liquid feed mixture which is having 5 components. You want to separate one product which is having highest boiling point, so that will be obtained from the bottom, and rest all the components will be obtained as distillate. So there can be another way also, like if you want to extract the product which is having some intermediate boiling point, so that will be intermediate cut in the distillation column, or depending on what type of product or at which boiling point you want to recover the product, you have certain cuts in the form of distillate, intermediate products, and the bottom. So you can have any number of components in distillate, intermediate, cut, or bottom. So in distillation you can have multiple components as the overhead product. Next question is, the minimum reflux ratio for a given separation. The number of required plates will be dash. So distillation process can be operated in two ways. You can have feed, and there will be number of trays. So depending on what purity you need of the product, to decide the number of trays, and you extract certain amount of product which is distillate, and you return certain amount of recovered product to the original column. So that is nothing but reflux. So now there can be two cases. Like this reflux ratio is nothing but this is the distillate having certain flow rate in mole per hour, and there will be certain flow rate of this reflux also which is returning. So reflux ratio is equals to L by D. Now minimum reflux ratio, to find out what number of plates you require, what you do is you plot, this is the uh, like diagonal line, and this is the equilibrium plot. Y equals to certain x. This is the equilibrium plot of y in relation to the x. Okay, just a second. So, yeah, this is the equilibrium line, which is the relation between y and x. So now to find out the number of plates that is required for any distillation column, this is the bottom concentration that you require. This is the concentration required in distillate, and there is some feed concentration xf. So based on all the data points that has been given, you draw some operating lines. Okay, so say for example, this is the operating line, this is the operating line, like, sorry, and this is the feed line. So the point, this is the point of interaction, and the entire line that you are getting is the operating line. This is the feed point in the column, and to find out the number of trays, what you do, you just try to go this way, you do staircase. Okay, so each step is nothing but it is representing one plate in the distillation column, and this difference between this operating line and the equilibrium line is nothing but the gradient or the concentration gradient or gradient from the equilibrium, or how far our system is away from the equilibrium. So for example, more the system is away from the equilibrium, larger is the gradient, and better separation you will get. Okay, so there will be certain chance that if this is the equilibrium line, then this, like, minimum reflux will occur when whatever you are getting, you take out all that product, all that in the form of distillate, so you are not returning anything, so that you calculate from this point where there is no gradient actually. So at this point, since there is no gradient, you will require more and more number of plates. So what happens is, lesser the gradient, more number of plates will be required. So at certain point, there will be the case where there is no gradient, and this is the point. So at this point, it is nothing but known as minimum reflux. Okay, and at this point, what you can say is, ideally you require infinity or infinite number of plates, because since the system is already at equilibrium, to change the equilibrium, it is not possible for this particular given conditions. So for minimum reflux, you require infinite number of plates or trays. Now next case is for the reflux ratio. Same, this is the equilibrium line, and this is the diagonal line. So as I said, sorry. So the difference between this difference is nothing but the gradient. So larger is the gradient, you will have better separation. Okay, so what can be Another option, like this is the feed line and this is the distillate. So this is the intersection point. So minimum reflux will occur when you move towards the equilibrium line. So if you move continuously away from the equilibrium line, what will happen? The gradient will increase, and obviously since gradient is more, you will require lesser trays in the column. So because the separation is more because of larger gradient. So what maximum gradient can occur is nothing but what you do, you try to shift this line towards the diagonal line, and if the operating line coincides with this diagonal line, then at this point whatever reflux ratio you get obtained is maximum, and that is termed as total reflux. So you are not taking out any product out of the column. Okay, so in that case what happens is the number of trays that will be required will be minimum. So this is the correct answer. Now if you look into the actual scenario, since you are recycling all the product and you are not taking out anything, then the load on the reflux condenser and the reboiler load and everything will change. So in that case the load on the condenser will increase. Also product overhead product will be minimal, or you are not recovering any product, minimal or negligible. So what you do in the actual scenario, you do not need the cost the operating cost in the form of condenser duty and all to increase, or you do not want infinite number of trays in the case of minimum reflux. So what you do, you operate at some intermediate point where which is known as optimum reflux ratio. So this is the actual point where industries operate so that the cost is optimized. So if you have minimum reflux or maximum reflux, obviously the cost will be higher. So you choose certain point depending on what is required. So for the correct present question, the correct answer is minimum number of plates is required for total reflux. Moving forward to the next question, Freon group of refrigerant is non-toxic because there are various refrigerants like chlorofluorocarbons were emitted from various refrigerants, so which were replaced. Sorry. So nowadays the refrigerants which are used are fluorine based, which are aimed to have lesser emissions, because what happens is if CFCs are emitted in the atmosphere, then they deplete the ozone. So nowadays, Freon has replaced the conventional refrigerants and they are non-toxic. Now, commonly used refrigerant in commercial ice plant is dash. So, Freon 12 is obviously a refrigerant, but it is not in the commercial plants or industries. Air is a coolant, but if you want to use like in minus or very like chillant, if you want to use as chillant or very low temperatures, then air is not the viable option. What you use is ammonia. So in plants or in industries, you have ammonia chillants where you want to have very low temperatures, say for example 4 degrees Celsius or so, then in that case what you use is ammonia chillant. Ammonia is the chillant. In the drying of non-dissolving solids, at constant drying condition, the internal movement is dash. So, as I mentioned, drying of solid is nothing but to remove the moisture content of the solid. So, any solid, if you dry, has a certain amount of constant rate period, then there will be some falling rate period. So, why does such trend appear? So, for example, if you have a solid, then what happens is there is in the initial stage there is certain amount of or in a sufficient amount of water that is present, so that the water on the surface, which, like, since the evaporation takes place from the surface, an equilibrium is established between air and the solid surface, because we have enough quantity of water molecules inside the pores or in the solid. So what happens is, on the surface it has enough quantity and this remains constant, and that is why a constant rate is maintained for evaporation of same amount of water molecules. Now, after a certain period of time, since the water quantity decreases in the solid, gradually the amount of water that is present in the solid, it reduces, and the water that is going onto the surface, it reduces. So that is why the rate at which the water now comes out from this is less. So this corresponds to the falling rate period. Okay, and so what happens is, during the falling rate period, you see some internal motion of water molecules from this internal, like from the interior of the solid to the surface, where which is because of lesser amount of water observed after certain drying. So here the correct answer is during the falling rate period. The rate of mass transfer coefficient is affected by dash. So, the mass transfer coefficient is obviously dependent on the temperature of gases, because since the temperature, like for example, temperature, if it is increased, then obviously the gas will have higher energy, which will result in better or more mobility, which is nothing but mass transfer coefficient, represented by mass transfer coefficient. So you can say that with change in temperature or at higher temperature, you will have more mass transfer coefficient as compared to lower temperatures. So obviously temperature has a great effect on the rate of mass transfer or the mass transfer coefficient. So yeah, that's it from my side today. If you have any question, you can ask me, or otherwise we can end this meeting. If you do not have any question, I will stop the screen sharing, and I will end this meeting here. So yeah, thank you everyone for joining. Thank you.